In the previous video, we covered many important factorizations and how to use them to solve very unique and interesting examples. Today, we're covering algebraic equations. Make sure to stay till the end of the video, where we'll explore how to completely trivialize a complex equation using the techniques we learned today. Start off, let's take an example. In this problem, we're asked to solve for a. We have these three equations. A squared b is 4, b squared c is 3, c squared a is 18. So what should we do here? The first thing to notice is that it's actually symmetric, because notice how there's an a squared term, an a term, a b squared term, a b term, a c, and a c squared term. So there are actually two ways to solve this. Let's explore them both. The first way is substitution. Now, I'm sure you've heard of this to solve two variable equations, but the truth is, it can solve equations much more complicated than that. So how can we solve this with substitution? First of all, let's take a look at this first equation. How can we find the value of b in terms of a? Well, b equals 4 over a squared, since a squared times b is equal to 4. Now, can we plug this into the second equation to solve for c in terms of a? Of course we can. The second equation states that b squared c equals 3. So 4 over a squared times c equals 3, right? Because 4 over a squared is b. So what is c? C is 3 over 4 over a squared squared. Okay, this is just 3 over 16 over a to the 4th, because a squared is a to the 4th. And this is 3a to the 4 over 16. Now, what's next? Well, now what we have to do is plug this in to the third equation. We know the value of c in terms of a, so we plug it into the third equation. That's 3a to the 4th over 16 squared times a equal to 18. So from here, let's simplify. This will be equal to 3a to the 4th squared, which is 9a to the 8th over 256, times a equals 18. Let's cancel out a factor of 9 from both sides. And then we rewrite this as a to the 9 equals, because a to the 8 times a equals 2 times 256, which is 512. So a is just 2, because 2 to the 9 is 512. And that's our answer, because we're asked to find a. Now there's also another way, which you've probably also heard of, elimination. And we're going to use it to solve this, except we can't just add the equations up this time. We have to do something a little bit different. So like I mentioned earlier, the symmetry between a, b, and c. So let's multiply all three equations. A squared b times b squared c times c squared a. What do we get? There's two powers of a, and there's one term of a squared and one term of a, so a cubed. Or let me write it more clearly. So we have a squared b, b squared c, and then times c squared a equals 4 times 3 times 18, or 12 times 18. Now let's multiply this. We get a cubed, a squared times a, b cubed, b times b squared, and c cubed, c times c squared. And this is 12 times 18. Now what is 12 times 18? Well, a little shortcut you can use to do this is difference of squares technique. 15 minus 3 times 15 plus 3. And that's just 15 squared minus 3 squared, which is 225 minus 9, 216. So a, b, c is equal to the cube root of 216, which is just 6. Okay, we have this, but we still have three variables. We haven't eliminated any of them yet. can we maybe use this ABC equals 6 to eliminate a variable? Let's divide by this equation over here. The reason we're going to divide by this equation is it will eliminate c. So let's divide by b squared c, and b squared c is equal to 3, so we divide by 3 to the right-hand side. This becomes ABC over b squared c, which c's cancel, and then b cancels with the second b. So it's a over b equals 2. 6 divided by 3 is 2. So if a over b is 2, we've already eliminated one variable. And guess what? We have another equation in terms of a and b. A squared b equals 4. So now what? Let's eliminate b now. We multiply these two equations together. We get a cubed equals 8, since the b's cancel. And that means a equals 2. Comment down below which solution you liked more. But they both give the same answer. If you're enjoying what you're seeing so far, be sure to like this video and subscribe down below so you get notified when new videos are released. Okay, next problem from the AMC 12. X, y, and z are positive numbers satisfying x plus 1 over y is equal to 4, y plus 1 over z is 1, and z plus 1 over x is 7/3. What is the value of x, y, z? So let's go back to our list here. We've already explored substitution and elimination, where and it's not always used in the standard ways you might expect it to. You might often have to do some tricky manipulation to eliminate variables or substitute different variables in. There's some other techniques like adding, subtracting, multiplying equations, grouping terms together, finding common denominator. They all seem like simple techniques, but they can be applied in very unique and tricky ways. So in this problem, we're going to try using some of those techniques. So to start, what should we do? A common first approach might be to think, let's do some substitution, right? 1 over y equals 4 minus x. So y is 1 over 4 minus x. But it turns out this will only make your problem harder, because then you've got a bunch of very ugly terms in your expression. You would end up with a really large degree polynomial, which would not be easy to solve. So the thing is keeping your eye on the ball. We're asked to find the value of x, y, z. We're not asked to find x, y, and z, just the product. That's all we care about. We don't even need to know what x, y, and z are individually. So let's try finding x, y, z without solving for each variable. How can we do that? Let's multiply. Well, how can we get an x, y, z term? X, y, z. Multiplying equations. Let's multiply all three equations together. X plus 1 over y times y plus 1 over z times z plus 1 over x. This is equal to, well, now we just have to expand this out. So you can do it term by term and expand it out, but I'm going to show you a shortcut way to expand it. So first we have, of course, we have the x, y, z term. And then we also have the 1 over x, 1 over y, and 1 over z terms here. So if we multiply all of these three terms together, we get 1 over x, y, z. So plus 1 over x, y, z. Now there's some extra terms. We know that there's going to be a total of 8 terms in our expansion. 2 times 2 times 2. So you need 6 more terms. So what you can see here is that x times y times 1 over x. That's one more term. And also we have x times y times z, which we already counted, but we also can have x times 1 over z times z. Or we can have x times 1 over z times 1 over x. X times 1 over z times 1 over x, which is and also, finally, we can also have 1 over y, if this is a term we choose from this expression, 1 over y times z. Or we also have 1 over y times y times 1 over x. And then finally, we have the last term, 1 over y times 1 over z, 1 over y times 1 over z times z. So I showed it here just to be clear, but what you can notice is that this expansion is symmetric. So if you actually cancel these terms out, x and 1 over x, they cancel out. The z and 1 over z term, they cancel out. The x and 1 over x term cancel out. Y, 1 over y cancel out. And same thing here. And z, 1 over z cancel out. So we're just left with x plus y. We're left with y, x, and z terms. So plus equals x, y, z plus 1 over x, y, z plus x plus y plus z. And then also we have a 1 over x term, a 1 over z term, and a 1 over y term. So plus 1 over y plus 1 over x plus 1 over z. Okay, so now we want to find x, y, z, right? So how can we get rid of this extra term? First of all, we know what this value is, right? This is just 4 times y plus 1 over z is 1 times z plus 1 over x is 7/3, which is 28 over 3, right? So we know what this is, but we need to somehow find the extra terms. How can we do that? Well, look back at the original problem. It looks oddly familiar. We've got an x, we've got a y, we've got a z, we've got a 1 over x, we've got a 1 over y, we've got a 1 over z as well. Maybe we should add all three equations up. Because if we do that, we have, let's add them all up. We have y plus 1 over z equals 1, z plus 1 over x is 7/3. So if we add them up, we get x plus y plus z plus 1 over x plus 1 over y plus 1 over z equals 4 plus 1 plus 7/3, which is 5 plus 7/3. And 5 is 15/3, so this becomes 22/3. Okay, that's great. So again, we used the technique of adding the equations up because we saw, oh, we've got an xyz term, 1 over y, 1 over z, 1 over x term. We added them up, and we got 22 over 3. So now this is equal to xyz plus 1 over xyz plus 22/3, which is equal to 28/3. So that means xyz plus 1 over xyz is nothing but 28/3 minus 22/3, which is 6/3, which is just 2. That's interesting. So from here, we essentially have two ways to proceed. Let me show you the first way. The first way is to see, oh, xyz is our answer. So let's just say that xyz is our answer. We have a answer plus 1 over answer equals 2. This is just a simple equation. We clear denominators out, multiply by a squared plus 1 equals 2a. Rewrite this, a squared minus 2a plus 1 equals 0. And this is a binomial expansion, a minus 1 squared equals 0. So a equal to 1. Answer is 1. That's our answer, because a was answer. Now here's another solution that most people probably won't see, and that is, what number plus 1 over its number is equal to 2? 1, of course. If you just plug in 1, 1 plus 1 over 1 equals 2. So yeah, if you see that, that's great, but if not, don't worry, you can always just solve the quadratic. Okay, that was a very interesting problem that utilized these techniques. Remember, we added the equations, we multiplied them, and it's not immediately obvious that we did that because there's so many other things you can try. Sometimes you find a common denominator, but not always, because sometimes it can actually make your equation more messy. And the main thing is we don't always have to find every variable. Keep your eye on the ball, what you actually need to find. And we also use symmetry. So if there's symmetry, then you can multiply, you can treat them all, you can assume certain things about other variables based on what you found for previous variables. So another technique is smart substitution, which is another one we'll be seeing a few times. And last class, we also discovered common factorizations that are very useful as well. So what are some smart substitutions is a very useful technique. Let's see how it's used in this problem. We've got finding the positive solution of this giant, ugly looking equation. 1 over x squared minus 10x minus 29 plus 1 over x squared minus 10x minus 45 minus 2 over x squared minus 10x minus 69. That looks very messy, right? We've got 1 over a quadratic plus 1 over another quadratic minus 2 over another quadratic. If we clear denominators, we'd end up with a quartic, a 4th degree polynomial. And I don't think any of us know the quartic formula. So we'll have to resort to other smart methods. Specifically, smart substitutions. The thing here is to observe that these terms look oddly similar, don't they? I mean, after all, they're all x squared minus 10x minus something, right? So maybe let's make a substitution. Y equals x squared minus 10x minus 29. Let's rewrite our equation in terms of y. We've got 1 over y, right? Plus 1 over y minus 16 minus 2 over y minus 40. That's great. Now we can multiply our denominators out, because now we'll only end up with a quadratic, not a quartic. Let's do that. Let's multiply the whole equation by y times y minus 16 times y minus 40. Okay. So 0 times anything is 0, so right-hand side is still 0. Let's evaluate this term by term. Y times y minus 16 times y minus 40 times 1 over y. The y terms will cancel, so it's just going to end up with divided by y, so these terms will cancel. We'll just end up with y minus 16 times y minus 40. So next off, we have 1 over y minus 16. What is 1 over y minus 16 times all of this quantity here? Well, similarly, y minus 16 terms cancel, because what they cancel out. 1 is 1 over y minus 16, and 1 is y minus 16. We're left with y times y minus 14. And next off, we have minus 2 over y minus 40. So minus 2, we'll just take out that term. Minus 2 times what? Minus 2 times 1 over y minus 40 times y minus 16 times y minus 40. The y minus 40 terms cancel. We're left with y times y minus 16. And that is equal to 0. Now, let's just expand it out and see what we have. Y squared minus 56y plus 640, right? Because minus 16y minus 40y. Plus y squared minus 40y minus 2 times y minus 16, which is y squared minus 16y. This is equal to 0. So we've got, let's expand this term out here on the 2 times y squared minus 16y, negative 2 times that. Well, that's just going to be negative 2y squared plus 32y. Negative 2y squared plus 32y, because negative 2 times negative 16y is 32y. Now let's see what we have. Oh, look at that. Isn't that interesting? Negative 2y squared, y squared, y squared. Isn't that wonderful? We thought we would have a quadratic, but we now only have a linear equation. And that's even easier to solve. So now let's see what other terms we have. We have 640 minus 56 plus 40 minus 32y. Or let me write this in a way that's more clear. Minus 56 plus 40y, because of these terms, and then plus 32y. So 640 equals 96y minus 32y. We just subtract by just moving it to the other side, because this is equal to 0. This goes to the other side, and this becomes negative. So 640 equals 64y. So y equals 10. So therefore, 10, be careful, 10 is not our answer, because we're not asked to find y, we're asked to find x. But don't worry, it's not too hard to finish from here. We know that y is x squared minus 10x minus 29. So x squared minus 10x minus 29 equal to 10. And we subtract 10 from both sides, and we get a simple factorable quadratic. This factors as x minus 13 times x plus 3 equals 0. And we're asked to find the positive solution, so it's just 13. That's the answer for this problem. And as we see, a very powerful application of the smart substitution technique. Sometimes you can also use common factorizations, like I mentioned in the previous video. Now we're going to see another example of a problem from the AMC. So this is another problem that utilizes smart substitutions. So we've got ABC being a solution to the systems of equations. X cubed minus xyz equals 2, y cubed minus xyz is 6, and z cubed minus xyz is 20. The greatest possible value of a cubed plus b cubed plus c cubed is m over n, and we're asked to find m plus n. What this ABC thing means is essentially, over all possible solutions of x, y, and z, find the greatest possible value of x cubed plus y cubed plus z cubed, where a becomes x, b becomes y, and c becomes z. Let's explore how to solve this. Well, let's see what our equations are. Let's try to make some observations. We've got x cubed minus xyz, y cubed minus xyz, z cubed minus xyz. There is a lot of symmetry here. We've got all of them have x, y, z terms. And whenever you see that, that is always, almost always, a sign to do a smart substitution. Let's do this. Let's say that a equals xyz. And now, let's see what we have left. So x cubed minus a, right, because this is a, is equal to 2. So x cubed is a plus 2. Y cubed minus a is 6. So y cubed is a plus 6. Z cubed minus a is 20. So z cubed is a plus 20. Now you might be wondering, what was the point of that substitution? Now we have a 4-variable equation instead of just a 3-variable equation. Don't worry, we'll get another a in there somehow. We know a is xyz. How can we construct another a term and get rid of these x, y, and z terms, so our equation can only be in terms of a and nothing more? Well, x, y, and z involves x, y, and z, and we've got x, y, and z terms here. We'll multiply them. So if we multiply them, we get that a cubed, because x, y, z cubed, equals a plus 2 times a plus 6 times a plus 20. That's good. Now we just expand the right hand side. Now the trick here is we have an a cubed term, and now we count how many a squared terms do we have. Well, we have a times 20, so plus times 20 plus. We have a times 6 times a, so that's plus 6. And then finally we have 2 times a, which is plus 2. Now what about how many a terms do we have? Well, we've got a times 6 times 20, which is 6 times 20 is 120, so times 120, plus we've got, we also have the term where we have 2 times a times 20, which is 40a, so plus 40a. And finally, we have the final expression is where it's 2 times 6 times a. So that's plus 12a. So plus 12 all times a. And finally, the constant term, 2 times 6 times 20, 240. Let's simplify and solve. First of all, a cube cancel. Isn't that great? Now we have a quadratic. And that quadratic, 28a squared plus 172a, 120 plus 1 plus 40 plus 12 is 172, plus 240 is 0. And now all we have to do is solve this equation for a. We divide by 4 to get 7a squared plus 43a plus 60. Okay, so from here we have multiple options. So the easiest way is probably, in my opinion, would just be to use the quadratic formula, but I'm pretty sure you can factor this as well. Quadratic formula, negative e plus minus 43 squared minus 240 times 7 over 14. 43 squared, if you watched my square video from several years ago, is 1849 minus 7 times 240. 7 times 24 is 140 plus 28 equals 168. So 7 times 240, 1680. More mental math techniques that would be good to know. We just subtract, we get 169. The square root of 169, 13. And negative 43 plus or minus 13 by 14. And we look at the possibilities. They can be negative 43 minus 13 by 14, which is negative 56 by 14, equals negative 4. Or we can also have negative 43 plus 13 divided by 14, which is negative 30 over 14, which is negative 15 over 7. What do we want though? Remember, we always want to keep our eye on the ball, what we want. We want the greatest possible value of a cubed plus b cubed plus c cubed. So we essentially want for the solutions to the equations in terms of x, y, and z, the highest possible value of x cubed plus y cubed plus z cubed. Aha! We know x cubed, we know y cubed, and z cubed in terms of a. Their sum, 3a plus 28. 2 plus 6 plus 20. 3a plus 28, we want it to be as big as possible. So we choose the larger of these two, negative 15 over 7, of course. So negative 45 over 7 plus 28. This will be our answer. But so now all we have to do, let's move this here. From here, all we have to do is see that this is going to be 28 times 7 minus 45 over 7. 28 times 7 is 14 times 14, 196. So this is 196 minus 45, which is 151 over 7. And you're asked to find m plus n, so 158. The final answer for this problem right here. Another very clever smart substitution application. Next off, we have these bunch of practice problems which you can actually find in the free AMC 1012 book, link in the description. And now we'll move on to Vieta's formulas. And Vieta's formulas are very useful, both the quadratic and higher degree form, and they can simplify expressions that allow you not to actually have to find the roots. But if you want to learn about Vieta's, check out the video over here. Okay,